So, hi everyone. I'm Erik Jenelius. I will present myself in a minute. And today I will give a brief introduction to the topic of transport systems resilience, which is a very broad topic, almost as broad as sustainable mobility itself. But I will try to, as I said, give a brief introduction to the topic based on some work that I've been doing myself over the years. And I have had some help with different colleagues with this material. So I've given a couple of talks in the Unite Sustainable Mobility Forum previously. In case you didn't follow the previous occasions, I'm a professor at KTH, Royal Institute of Technology in Stockholm. And I'm interested in topics like public transport planning, urban mobility, micromobility, and not least, transport systems resilience, which I will talk about now. So starting off very broadly, what does the concept of resilience mean? It has different meanings and interpretations depending on which field you are active in, and so it has different origins and perspectives. But in one way or another, it is about how we handle large disruptions to a system. And one thing that distinguishes resilience analysis to, let's say, more traditional risk management methods that have been used in transport and other areas is that in traditional risk management, we typically assume we can assign some probabilities and consequences to different scenarios. But in resilience analysis, we take a bit broader scope, and with large disruptions that occur very rarely, we know very little about what the probabilities are and also what the consequences will be. Typically, there would be no similar historical event that we can use as a benchmark to say what exactly the consequences will be. So it can be various types of disruptions. We have the natural hazards like extreme weather or earthquakes or floodings. We have climate change, which can also be a cause of some of the natural hazards. Then we have the more deliberate attacks like cyber attacks or physical sabotage to the transport system, which can range and include acts of terrorism and even war. And also things like the pandemics, like the COVID-19 pandemic, which is still fairly fresh in our memories, which had major impacts on the transport system. And being resilient against one of these types of disruptions doesn't necessarily mean that we are resilient to another. Let's say to be resilient to COVID-19 could meant, for example, that we had large supplies of face masks, which would be fairly useless in the scenario of large power outage, for example, which would then it has to do with spare capacity, backup options for power supply, which is quite a different way of being resilient. If we look more specifically at the transport system, still there are many different definitions, but this is one that we proposed a couple of years ago, and it focuses on both reactiveness and proactiveness. So we say resilience is the ability to prepare for and to withstand, absorb, and adapt to shocks, and to recover from the consequences in a timely and efficient manner. So we can see there are 3 phases in a disruption process. We have the before, we have the during, and we have the after. And in each of these phases, there are ways to increase our resilience to disruptions. There have been proposed 4 main strategies of being more resilient. One is having redundancy in the system, that we have backup options, more of the same. We can think of a transport network where we have more than one route from origin to destination. So if case there's a blockage of one rail line, there might be another rail connection that we could take instead. Flexibility, the ability to choose different ways of doing things. Agility, which is similar, but also stresses that we can adapt fast and quickly in response to a disruption. And collaboration, which is basically saying that we are better in dealing with disruptions if we collaborate, if we are more doing it together than each of us trying to manage on our own. Yeah, and various studies have tried to break down the resilience concept in different ways. One way to do it is to distinguish between static resilience and dynamic resilience. So static resilience is the capability to maintain the functionality when facing shocks. And dynamic resilience has to do with the response and the recovery, how fast we can return to a new equilibrium state after a disruption. Another way to break down resilience is to do it in terms of 4 properties of resilience: robustness, redundancy, resourcefulness, and rapidity, sometimes known as the 4 R's of resilience. We see they are a bit similar to the 4 strategies that I mentioned earlier. We have redundancy here as well. And again, the rapidity is being stressed here, how fast we can recover. One common way of illustrating resilience is through a diagram like this, where we try to we imagine that we can evaluate the performance level of a system in some way. So we have some normal level of performance before there is a disruption. Then a disruption occurs, so the performance level drops. The disruption ends, and we enter a phase of recovery. So the performance level goes up again. And finally, we reach a new normal state, which might be the same as before, or hopefully not, but could be worse, or even better, we could reach a better state than what we had before. This figure also highlights these different phases of the disruption, the before, the during, and the after phase. In this way, we could make a distinction between robustness and resilience, so we can view the robustness of the system as the level of performance that we can maintain even during disruptions. Whereas resilience both is the static aspect, the robustness, but also the dynamic aspect, how fast we recover from the disruption. So the combination of those two is basically the area here, the total performance loss that we get from the disruption. So disruptions to the transport system can occur in different ways. I think a pretty useful model of the transport system in this context is to view it as different layers. So at the bottom, we would have the infrastructure, the roads and the rail lines, etc. On top of that layer, we have the transport services, which are the public transport routes, rail lines. We have the shippers of goods, etc., that use the infrastructure to move people and goods. And on top of that, we have the actual travelers on the system. We have the actual goods that move with the help of these services. And we also have another layer, which is the management layer, where we have the planners and policymakers that make different type of decisions that can influence all the three different layers. And in terms of resilience, we can have disruptions in all of these different layers. The infrastructure itself can be disrupted. We can have technical failures. We can have power failures that means that the trains cannot run. We can have extreme weather. We can have floodings of the roads and the rails. We can have deliberate attacks that disrupts a bridge or things like that. But then even if the physical infrastructure works, there could be disruptions in the services. For example, strikes, human errors, and other types of disruptions. At the demand level, there can be, for example, special events, big sports events that causes a surge in travel demand that could cause a standstill in the transport system. There could be things like the pandemic that caused a big drop in the demand while the infrastructure was more or less intact. We can even have disruptions in the management, like a sudden shift in policy, for example, that could propagate into the transport system. And also a disruption that starts in one layer could propagate and spread into the other layers. So there can be complicated cascading effects throughout the transport system. So here is just a few examples of real world events, big disruptions, taking from different modes of transport. So there can be things that affect maritime transport, like rough weather that This is a passenger ferry that sank in the Baltic Sea in the 1990s. We have examples of terrorist attacks on the rail network in the 2000s. We have extreme natural hazards like the volcanic ash cloud, earthquakes, hurricanes, extreme rainfall, just to take a few examples. Our different modes of transport are different. They have fairly different characteristics that also affect how resilient they are to disruptions. Road transport, I would say, is characterized by relatively high levels of independence for users. We as travelers have quite high flexibility on our decisions, where to travel, when to travel, etc. And there are typically more than one route to go from one place to another in the road network. So users are fairly well equipped to handle disruptions, but remote areas can still be vulnerable to disruptions at particular critical locations, for example, a bridge to an island and so on. Also in urban areas, they can be quite vulnerable to cascading congestion and queues in case there is a traffic accident or something that blocks an important road. Rail transport, on the other hand, is fairly sensitive to disruptions in general. It's a much more regulated and controlled system, which means it's more rigid and less flexible to change operations in case there is a disruption. It's more dependent on other critical infrastructure like the electric power, ICT systems, mechanical, electrical systems. So there are more things that could go wrong in general in the rail system than in the road transport system. In combination, that the redundancy in the routes is typically lower. So if one train has stopped, it's more difficult for other trains to pass that train and more difficult for passengers to find alternative routes to their destination. Air transport, I would say, is characterized by very high safety and security concerns. So they have a lot of protocols in place to handle different types of threats. But it has a strong private market competition, strong dependencies on labor, fuel supply, and other systems. We know it is sensitive to, for example, labor conflicts, strikes, and so on that can leave the planes stranded on the ground instead of being up in the air. So they are quite restricted in the nodes, meaning that all planes have to start and land at certain airports, whereas up in the air, they are much more flexible in terms of the routes and the speeds of the flights. So they are a bit flexible in that sense to avoid bad weather and so on. So the disturbances tend to be originated at the nodes, which can cause a lot of knock-on delays, missed connections, so on. One way I think can be useful to measure the performance loss in a transport system. If we remember this resilience curve that I showed before, we should have some measure of system performance or system function. One way to do that could be to measure it in terms of how well the supply, the transport supply is able to meet the transport demand. So in normal circumstances, hopefully the supply in terms of capacity in the road network and the rail network and so on can reasonably well handle the travel demand. But in case there is a disruption on the supply side, then capacity goes down, and then we are not able to accommodate all the demand that wants to use the network. And this would lead to a loss of function for a while until we can recover the supply level back to normal. So transport infrastructure can be disrupted in many different ways. I alluded to it already a bit, but we can have some type of disruptions that are natural, meaning they are caused by nature, like disasters, extreme weather, so on. We could also have technical failures in the infrastructure. Then we have disruptions that are caused by humans, but are unintentional. So we have accidents, handling errors, negligence. And finally, we have human-made disruptions that are intentional, where we have some form of antagonist that wishes to cause harm to the transport system. That could be a labor market dispute, but it could also be criminal activities. It could be terrorist attacks or even acts of war. Some disruptions originate within the system itself, whereas others originate outside of the system. Extreme weather is a common cause of disruptions. And there can be many types of extreme weather. And different modes of transport are sensitive to different types of extreme weather. Heavy snowfall, for example, well, there are a few transport systems that are completely robust to snowfall. Roads can be blocked, icy and slippery, rails as well. You could also have electricity losses due to snowfall. Airport runways can be blocked, etc. Heavy rain can cause floodings, but also that roads or tracks are washed away. Drought can lead to forest fires that causes blocking of roads and rails. Heavy winds can affect waterway and air transport, and so on. Another type of disruption that hasn't been, I would say, analyzed as much as infrastructure disruptions or supply side disruptions are when something happens on the demand side. So in this case, the supply side, the capacity of the transport system would remain the same, but we would have a sudden, either a short-term or a long-term change in travel demand. That means the supply cannot meet the demand. So in the short term, we could have, for example, a special event like a concert or a sports event that causes a sudden surge in travel demand that the system cannot handle. Or we could have a more long-term increase. Let's say we have a trend of sustainable mobility, meaning that more people choose to go by train than by car. That could mean that the demand for rail travel increases, and the supply might not be able to accommodate for that. We can also have disruptions when demand decreases, and demand could decrease on the short term. Let's say if there is a threat of terrorism or a threat of bad weather, then demand could suddenly go down. But also in the more long term, we have, like, for example, the pandemic that caused a drop in travel demand that lasted over several years, and even we feel today this drop in travel demand. And this drop in the short term might not lead to any drop in functionality of the system. If the supply remains at the same level as before, then the system doesn't have a problem handling the demand. But an issue could arise if we reduce the supply in response to the drop in demand, and then demand goes back up again after some time. If supply is not then able to respond to that recovery of demand, we could be in that situation that we have a demand that exceeds the supply. Yeah, so COVID-19, I think, is a good example of a long-term drop in travel demand. These figures shows how the number of trips in the rail system in Sweden changed between 2019, which was the year before the pandemic, and then during 2020, which was the first year of the pandemic. So we see a sudden, very big drop in the number of trips. Whereas on the supply side, most of the trains continue to run as normal. The supply remain much more constant than the demand. Okay, so how can we analyze the resilience of a transport system? There have been different approaches that have been used. One approach is to try to draw some conclusions based on the structure of the transport networks. So I mentioned that, for example, the road network is generally more resilient than the rail network because there is more redundancy, more alternative routes. That's something we can analyze through the topology or the structure of the networks. So we can quantify the redundancy of the networks by looking at the network structure. And we can identify critical points in the networks, where for example, we have bridges that connects one side of the network to the other side. So those points would be very vulnerable to disruptions. A bit more sophisticated is also to look at the flows through the network. So where the travelers go and the goods go and so on. That tells us a bit more about what the consequences would be if there are disruptions, and how they could reroute to other alternatives in case there is a disruption. If there are alternative routes, then that's good. If there are no alternative routes, that means that there are some travelers or goods that cannot reach their destination. So probably the consequences are very high in that case. Another level of sophistications would be to go to more sophisticated models of the transport system, like agent-based simulation models, for example, where we try to model individual travelers and their decisions. And then we could simulate a disruption in the system and see how these agents respond, how they find what to do if their normal options are not the same or not available anymore. Game theory, I think, is an interesting area that can be used to understand resilience, especially against intentional attacks. Probably an antagonist wants to achieve the most damage as they can, so they try to find vulnerable spots in the system. And if we try to protect the system, then we try to protect those vulnerable spots in the first case. Then maybe the attacker will try to find other locations. And we can apply sort of game theory concepts in trying to understand how those interactions would work out when we try to protect the transport system as good as possible. So how can we increase resilience? Well, we can come back to these strategies that I mentioned in the beginning. We can work to increase robustness. And how we can do that, we can make the infrastructure more robust. The roads, the bridges, the railways, the drainage, not least, like the water pipes under the roads and rails and so on, so that they can withstand and absorb external shocks better. We can improve the inspection, repairs, maintenance. Redundancy, we can improve by adding more links, increasing the number of alternative routes. We can simplify that different transport modes can substitute for each other. If one mode goes down, then the other could serve as a backup. We can have better planning to have spare capacity for both personnel and vehicles in, for example, public transport, so that they can jump in and cover for if there are suddenly people sick or technical problems. Also, we can work on improving resourcefulness and rapidity. So we can improve our capacity, our level of readiness to have relevant equipment and trained personnel on standby, to have proper information systems, to have quick response in case something happens, and to provide the travelers with relevant information so they can make better decisions on their own how to act. Yeah, so these are a few examples taken from a study on examples of how to enhance the resilience against flooding in particular. Both proactive actions as well as reactive actions. And these are some examples from another study from the Department of Transport on preventive actions to enhance the resilience to extreme weather events. And when we're talking about demand losses, we can also be more resilient to that. We can, we can try to reduce the demand loss. Some examples from COVID-19, if we worked on increasing the cleanliness of the vehicles, enforced social distancing, crowd management, etc., then we were able to allow more people to continue traveling with public transport than they could have otherwise. The supply can be more responsive, adaptive to fluctuations in the demand, or simply we can be more tenacious in the supply. Even though demand drops, if we are able to maintain the same level of supply, then we can make sure that we will have enough supply when eventually the demand comes back to the normal level. There are many ongoing trends that I would say will impact the resilience of the transport system in the future. Technological development is an important one, like the introduction of connected autonomous vehicles. The vehicles start communicating with each other, with the infrastructure, and so on. They could become maybe more vulnerable to some things like cyber attacks, but maybe more robust to other things. If, for example, they have more information about traffic accidents that have happened and bad weather and so on. Electrification is another big area that will for sure influence the resilience. I think that's worth a talk on its own, that we probably will have higher dependence on the power system, but also less dependence on fossil fuels and so on. Climate change, of course, will have big impacts. COVID-19 has taught us a lot of what can happen on the demand side of pandemics and similar happenings. So I'm reaching the end of the talk, but I want to end by broadening this perspectives just a little bit. I have talked mainly today about resilience from an engineering perspective. I have based it around this resilience curve on the left here, where we say that we assume that we can measure system performance in some way and measure the drop of performance and the increase of performance again. There are other perspectives of resilience where the perspective is not that simple, but for example, in social ecological resilience, we have sort of more the viewpoint that everything is constantly in flux and changing. We can have a system that is under various strains, external strains. So resilience is more about the ability to adapt to external strains and evolve, but not really to come back to some previous level, but how the system can evolve over time and hopefully into something even better than it was before. I think that perspective is quite useful, especially for long-term disruptions like the COVID-19 pandemic, for example. When the impacts have lasted several years, I think it's fairly meaningless to talk about returning to the same state as before the pandemic, but rather how the transport system can evolve into something again, relevant and useful, but not necessarily the same as before. So we are working on developing methodologies for understanding resilience from the social ecological point of view. And we are applying that to public transport in an ongoing project. Just to wrap up, I think one feature that characterizes resilience analysis is that we have to deal with a lot of uncertainties. What will happen in the future? So the transport system is constantly changing and evolving. As we said, we don't know what the future system will look like with new technologies and policies, etc. And we also don't know what the threats will be in the future, how climate change will evolve, how the geopolitical situation will evolve, etc. So we have a lot of challenges when we try to analyze resilience. We need to handle uncertainty, deep uncertainty. As I said, we cannot really put probabilities on different things, but our uncertainty is more deeper than that. So we probably need to work with other types of tools. Scenario analysis, I think, is an important one, where we try to map a wide set of possible future scenarios and see what would be the impacts of disruptions to the system in different future scenarios. And then we can apply different tools for decision making under uncertainty to see which actions to increase resilience would be useful under a large set of future scenarios. That might be strategies that we should go for. So to conclude, I've talked about the resilience of the transport system. So I defined it as the ability to prepare for and to withstand, absorb, adapt to shocks, and to recover from the consequences timely and efficiently. The transport has a key role for other infrastructures. I didn't emphasize this, but also if there are disruptions in the power network or the water network, then you need a transport system to go out there and repair that. So we have a wide range of different disruptions that could happen, different causes. The different systems are quite different in their characteristics. We have some different tools that we can use to study resilience that can help identifying vulnerabilities and evaluating measures to enhance their resilience. But now we also need to implement the findings from research into practice in order to make the transport systems more resilient. Thank you. That's my talk for today. And now I'm happy to try to answer in case there are some questions.